Hey everyone, Big Mac here. So I decided let's do another QualQuest video today. Obviously, like I mentioned, I'm going to start doing it from the second day of the harder, some more or less problems. So this is the one we're dealing with today. We have a continuously differentiable function. That means that it is constantly smooth, and no matter how many derivatives of it you take, you'll have a nice smooth function without any jumps or gaps or what are those things called? Cusps. Basically, we have this condition: f squared plus f prime squared is greater than 1 for all x in a certain bounded set. Now we have to show that within this bounded set, that f can only have a finite number of zeros. So instead of trying to prove this one directly, what we're going to do actually is do it from the opposite direction and show that the opposite cannot be true. So if we assume that there are an infinite number of zeros on a bounded function, then we're going to look for some kind of contradiction regarding our earlier conditions. Either that it doesn't satisfy our inequality, or that the function is not continuously differentiable. So without a loss of generality, I'm just going to say that our bounded set is from 0 to 1, so we don't have to worry about that too much. But basically, again, assume we have an infinite number of zeros in this small range. So, for example, you could consider that at every fractional point you have a 0. So you could have 0 1/2, 7/8, whatever. Obviously, there will be an infinite number in this range, so that would satisfy our condition. Exactly where the zeros are is not important, but I'm just trying to illustrate where they could be. So we need to try and find some kind of sequence that is going to contradict itself. So let's let y sub i, be some sequence of zeros that converges to some point y within our set. So, for example, we could have y1, y2, and eventually they converge to some point y. Let's use another sequence, z sub i, and basically where we want each z sub i to be in between the two consecutive y points. So z1 would be in between y1 and y2, etc. Okay, so another theorem that we're going to use here, we could either use the mean value theorem as a specific case, or in general, we can use Rolle's theorem. Basically, that says that for any x, that if you have two endpoints that have the same value, in our case 0, then for a continuous function, there has to be at least some point in between such that the derivative at that point is also 0. Which makes sense, because in order for a function to go up, it has to come back down somewhere. So we can choose this point where our derivative is 0 to be our zi. But if our derivative is 0, then going back to our original inequality, we then know that the absolute value of that f of zi has to be greater than or equal to 1. So we might come up with a problem here. Alright, so here is where we have a bit of a problem. Like we mentioned earlier, is that our sequence yi will converge to our point y. So obviously, as we take the limit as, I guess I can make these n's, sorry, doesn't really matter too much. Or make these all i's, switch my n's and my i's around, I suppose. Sorry about that. But anyway, if we take our sequence of y n's, obviously we'll converge to y. But since our z n's are also trapped between our consecutive yi's, then they also have to converge to the same value of y. But the problem is, with our function, we noted that each f of yn was 0, and yet each f of zn had to be greater than or equal to 1 by absolute value. So basically, as we approach our point y, we're saying that it has to equal both 0 and 1 simultaneously, or at least 1, or greater by absolute value. So then, there's no way that this function can be differentiable, and thus this contradicts our notion that there could be an infinite number of zeros, and thus we can only have a finite number of zeros. So it's kind of a roundabout way to solve it, but it works. Alright, Big Mac Sam.